Hello, this is the refrigeration presentation. This is section 6, and the team members are Wesley Hobbs, Taylor Roos, and Pei-Ya Wu. To begin, we'll start with the background. There was a cooling system developed by Machine Chillers Incorporated. It is based on the vortex tube that uses air as a working fluid, and our objective for this lab is to model and determine the system capabilities of what Machine Chillers developed. Now, of course, there are going to be multiple components to this. Initially, we're going to look at the steady state analysis for the different pressures that we use for each of the components. Next week, we're going to dive into the transient response, which we'll touch on more later. But for this week, it's just the steady state part of the code, or of the results from the data. And the different components are the vortex tube, the motor/compressor, the heat exchanger and accumulator. And finally, we're going to look at the ambient temperature and thermal resistance. And before we dive into what we did and what the results were for the week 1, we're going to describe to you just briefly here the experimental setup. What we did is there were 5 stations. Station 1, it starts with compressing the air. By the time we get to station 2, the air is also cooled to an ambient temperature. At station 3, the air has been stabilized. And finally, it splits off and ends up either at 4H or 4C. Either it'll be a heated temperature or it'll be a cool temperature, the fluid, which in this case is the air. And then finally, we get to station 5, which simply is a point where we analyze the fluid before it exits the system. And to break that up a bit more, we divided up here all the different components to this lab for week 1. The first is we look at the vortex tube. We collected data for 0, 40, and 80 psi. We were actually given data for 20 and 60. And then we also modeled the steady state relationships for these different values here, as you can see on the slide. And then also collected these different temperature values at each of those pressures. Similarly, for the motor and the compressor part, we generated code based on the 0, 20, and 40 psi. With the compressor, we also developed we showed the relationship between the motor speed, generated pressure, and finally we collected those 2 temperature values, which you can see in the diagram, the slide 3 where the intro was. And then finally we have the exchanger and accumulator, where from this we can find the energy from the exchanger that was given, and the accumulator from the compressor data. Results we plotted versus pressure, and then lastly we determined the ambient heating and thermal resistance at steady state. We simply took the vortex tube data and found that ambient temperature, and then also found the thermal resistance and compared it to what we expected theoretically.
To start our analysis of the system, we first want to look at the vortex tube. The vortex tube serves to separate the accumulator's output into hot and cold outputs. The hot and cold output flow rate data was collected along with temperature and pressure data across multiple nominal pressures. The first nominal pressure was 0 psi. In order to analyze the system, we first identified the steady state pressure. We first looked at the 0 psi nominal pressure. As seen, this system never reached steady state, but the system was used to determine the sensor offsets, which is important to consider in all nominal pressure analyses. These offsets were calculated under a couple of assumptions. There is 0 initial flow out of the vortex tube. The pressure sensor initial reading was the ambient pressure of the room, and the temperature sensor's initial reading is the ambient temperature of the room. Given these assumptions, the offsets shown here were tabulated and accounted for in further calculations. In a similar manner, data at 20 psi nominal pressure was analyzed. Based on the pressure data collected, a steady-state pressure of around 220,000 newtons per meter squared was reached within the first few moments of data collection. There is a good amount of confidence in the steady-state value since there was small variation after this value was reached. The relationship between the P3 pressure and vortex tube output temperature and flow rates were analyzed. As seen, the data was plotted and modeled using a York regression. A linear York regression did go through the data and did characterize the overall trend of the data, but the regression did not accurately portray the variation within the data collected. As seen, there is a negative correlation between pressure and the cold temperature, while there is a positive correlation between the hot temperature and the pressure. In both temperature scenarios, there is a positive correlation between pressure and flow rates. Data at a 40 psi nominal pressure was analyzed. Based on the pressure data collected, a steady-state pressure of around 326,000 newtons per meter squared was reached within the first few moments of the data collection. There is a good amount of confidence in the steady-state value since there was very small variation after the value was reached. Again, the relationship between the P3 pressure and the vortex tube output temperature and flow rates were analyzed, and the same trends were seen here. The same process was carried out for the 60 psi nominal pressure, and the steady-state value was found to be around 486,000 newtons per meter squared. There is high faith in this value since there is little variation outside of this value. The relationship between the P3 pressure and the vortex tube output temperature and flow rates were also analyzed here, and the same trends were seen. Finally, the process was carried out one more time at 80 psi nominal pressure. A steady-state pressure was found to be around 580,000 newtons per meter squared, which is fairly reliable since there was very little variation outside of this value. The same relationship between P3 pressure and the temperature and flow rates were also seen at this nominal pressure, but even more dramatic than the other scenarios. All data collected thus far has been driven by only a pressure regulator. Moving forward, we would like to see the effects of a motor-driven system. A compressor was added to the system, and the same steps were once again carried out to analyze the system. The 0 psi nominal pressure data collected was used to recalibrate the sensor offsets. These values are shown in the table and accounted for in later calculations. The 20 psi nominal data reached a steady-state pressure of around 244,865 newtons per meter squared. This data is more jumpy than the non-compressor data, so there is less trust, but the value is still fairly reliable since there is no major spikes. The 40 psi nominal data reached a steady-state pressure of around 351,000 newtons per meter squared. This data is more jumpy than the non-compressor data again, so there's less trust, but the value is still more reliable since there are no major spikes. The 60 psi nominal data reached a steady-state pressure of around 524,000 newtons per meter squared. This data is fairly reliable since there are no major spikes. The major conclusion from this analysis stems from the relationship between motor speed and P3 pressure. The steady-state value for the three scenarios previously mentioned were plotted against their respective motor RPMs. There is a positive correlation between motor speed and pressure, so as RPM increases, pressure also increases. More data points at different nominal pressure scenarios should be collected to determine a more detailed relationship between the two variables. The compressor has a positive correlation to the pressure, but obviously energy is required to drive this compressor. In order to determine whether the compressor is truly beneficial to the system, the energy used to power this compressor was tabulated. Using the data collected from the compressor integrated system, an energy balance was applied. Under transient assumptions, the energy transfer within the air is equal to that of the mass load. Using the equation shown, the energy transfer was determined for the nominal pressures. The data provided failed to include the flow rate data for a 40 psi nominal pressure. The regression determined from this data is unreliable due to the lack of data points tabulated. Based on the data given, it is beneficial to have the compressor. The energy required to operate the compressor is low, while the effects of the compressor on the pressure and the overall system is high.
Using the vortex tube tests, the ambient heating is determined for the non-compressor cases. The experimental thermal resistance calculated with the equation shown here, with the resistance equal reciprocal of the ambient heat times the temperature difference between ambient and the aluminum block. The experimental resistance is shown here in the chart for each of the different nominal pressure. The theoretical value of thermal resistance using thermal conductivity, thickness of insulation, and size of the aluminum block is also calculated here on the right. By comparing them, we can observe that the experimental value is quite off from the theoretical result. by an exponential amount. This might be due to the assumption we made in the calculation for the heat transfer rate due to ambient heating. At steady state, we assume Q load equals 0, so then Q air equals Q ambient, and real-world examples might not be so ideal. Another explanation might be that the friction during the airflow might also stop some of the heat transfer from being entirely calculated. In week 2, we would expand more on the steady state analysis, but in week 1, we would put in the transient analysis for the refrigeration load. We would model the transient cooling of loading by analyzing the thermocouple data at ambient pressure, ambient temperature for 40 and 80 psi. We would also measure the temperature for them at each state. Later in the report, we would have uncertainty analysis on the refrigeration load with transient and steady state findings. These uncertainty will be determined so that we can explain discrepancies between model and results. They might be due to sensor uncertainty or model errors in some assumptions we made about the model. So these will be calculated specifically, and that they can offer a good conclusion as to how sure we are about the refrigeration model we presented here. So with all the data collected and the plots shown, we can conclude that the mass flow rate versus pressure is not suitable for a linear York fit with a lot scattered around. The steady state line pressure is found for each nominal pressure cases, and the compressor work and a pressure linear relationship can be found, and so does the ambient heat. And the takeaway point from here, we can see that motor speed and nominal pressure has a linear relationship, and we can see that the pressure is needed for the refrigeration system. Also, ambient heat at steady state and experimental refrigeration load is characterized well in this case, but more transient state analysis and uncertainty is needed to draw further conclusions on this system.
And then finally here we have the references. Thank you so much.